In this video, we are going to finish up Chapter 5, Section 5.2, where you're going to be learning about binomial probability distributions. Your objectives here are going to be to determine if a probability experiment is a binomial experiment, find binomial probabilities, and find the mean, variance, and standard deviation of a binomial probability distribution. According to a recent survey by Pew Research Center, about 85% of adults know what Twitter is. Suppose we have a room with 10 randomly selected adults. We ask each if they know what Twitter is. What is the probability exactly 8 of them know? What is the probability that between 6 and 9 of them know? And what is the probability that at most 5 of them know? So let's define X to be the number of these 10 adults who know what Twitter is. Then X is going to be a random variable, and we can construct a probability distribution for X. So how would we find that the probability X equals 8? So first, we need to find out how many arrangements we could make out of 10 people where 8 know what Twitter is. And then we need to find the probability for each of those arrangements. Doing a process by hand like this would take a lot of time, but there is an easier way, and that's what we're going to be looking at. So this type of problem is called a binomial experiment, and it involves what's called a binomial random variable. This lesson is going to discuss an easier way to find probabilities associated with binomial random variables. A binomial random variable has 4 criteria that must be true. There are a fixed number of trials or observations. The trials are independent. Each outcome can be classified as either a success or failure. The random variable is counting successes. And if any of these are not true, then the distribution is some other type of probability distribution, not a binomial distribution. So looking back at that Twitter example, is it a binomial distribution? Remember, it says 85% of adults know what Twitter is. A room has 10 random adults. We ask each adult if they know what Twitter is and count the number who do. Are there a fixed number of trials? So remember, a trial here is asking one of the adults if they know what Twitter is. So there are 10 trials. Are the trials independent? Since the adults are randomly selected, the trials are independent. Are there only 2 possible outcomes? So when they ask one of the adults, the adult will answer either yes or no, and we will call yes a success. So yes, there are only 2 outcomes. And are we counting successes? So we are counting the number who do. So we're counting how many of the adults say yes. So yes, we are counting successes. And you can see all 4 are true. So this is a binomial probability distribution. S means the trial is a success for an individual trial, and F means the trial is a failure for an individual trial. Since S and F are complements, then we could say the probability of S plus the probability of F should give me 1. We will refer to the probability of S and the probability of F often, so we're going to let P mean the probability of success and Q mean the probability of failure. Q will always equal 1 minus P. N means the number of trials in the experiment. So looking back at the example of the 85% of adults know what Twitter is, a room has 10 random adults. S means the adult knows what Twitter is. F will be the adult does not know what Twitter is. N in this case would be 10. Our probability of success is 0.85, which means the probability of failure, or Q, is 0.15. X is the number of adults in the room of 10 who know what Twitter is, and X can be any whole number 0 to 10. Okay, if I have the probability X equals 8, that means the probability of exactly 8 of these 10 adults know what Twitter is. Here, let's look at an example of withdrawals. We have a certain college states 31% of withdrawals occur because the student has employment conflicts. A random sample of 20 withdrawals is selected and the number which had employment conflicts is determined. Here we're going to look at two questions. Is the situation a binomial experiment? And you're going to justify using all four criteria in context. And if so, specify the values N, P, and Q and list all the possible values of X. So the first thing we want to look at is this situation a binomial experiment, and justify using all four criteria in context. So we want to look, does this have a fixed number of trials? So a trial in this situation means one student's reason for withdrawing is determined. So there are 20 trials. The 20 trials are independent because they're randomly selected. The result for each trial is either success or failure. So here we're going to say that the success is withdrew because of employment conflict. And a failure is the student withdrew not because of employment conflict. Okay, so some other reason than an employment conflict would be your failure. And then your last thing that we have to look at is X counting the number of successes. So yes, X is counting the number of students who withdrew because of employment. And that is the number of successes. Now we can specify the values of N, P, and Q and list all the possible values of X. So for N, it is the number of trials, so we have 20 trials. P is the probability of success. So if you think back to what the problem said, it said 31% of withdrawals occur because the student had employment conflicts. So this is going to be 0.31. Q is going to be 1 minus 0.31, so you should have 0.69. And X can be any value from 0, students withdrawing because of employment, 1, 2, all the way up to 20. So what we're saying here is there could be no students that withdraw because of an employment conflict down here, all the way up to all of them withdrew because of an employment conflict. We use the word success and failure without regard to the desirability of the result. So in probability, success simply means the event of interest occurs, and failure means the event of interest does not occur. Always make sure P is consistent with what you're actually counting. So for example, an intensive care floor of a hospital, there may be 5 patients with a serious condition who have a 70% chance of dying. We may choose to count the number of these patients who end up dying. Since we're counting deaths or patient dies, is labeled success for the purpose of talking about the probability, and P would be 0.70. That does not mean that we generally consider patient fatalities desirable, but that's what we're counting in this case. Let's look at a marble example. So we have a bag contains 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select 3 marbles from the jar without replacement. From the ones you drew, the number of red marbles is counted. So is this situation a binomial experiment? We're going to justify using all 4 criteria, and then we'll be able to label those pieces in PQ and list it all the possible values of X. So why don't you pause the video here and try this example, and then when you come back, you'll be able to see those answers. So for that marble example, it did say that you randomly select 3 marbles from the jar without replacement. So when we have that without replacement, that actually makes it no longer independent. So the probability of selecting a red marble on the first trial is 5 out of 20, but because it's not replaced, then the probability of successes being red for other trials is no longer 5 out of 20. So because those trials are not independent and the probability of successes does not stay the same, this is not a binomial experiment. But if we replace the marbles, would this be a binomial experiment? So if you think about it, our trials would be the 3 marbles. So we have a number of trials. We have a independent because we are replacing the marbles this time. We have the counting the number of successes. So successes would be that the marble is red, and we can label successes as being red or not being red. So it would be a binomial experiment if it was just changed to we replace the marbles. So you should be able to do the following. Given a situation, explain whether or not it's a binomial experiment using the 4 criteria in context. Construct a binomial probability distribution and its graph. Answer probability questions and find the mean, standard deviation, expected value, and the range of usual values. So constructing a probability distribution, the easiest way to represent a binomial probability distribution is to create a table and then make the histogram of the probabilities. So in Excel, you're going to create the column listing for all the possible values of X, and in the column to the right, create a column listing the probabilities for each X. We did this in the previous section, so you should feel comfortable creating those probability distributions. There are several methods for finding binomial probabilities. You can see here there are 3 methods we will not be doing, but we will be using technology. So in Excel, you will be using a new formula, and it is binom.dist and binom.dist.range. Now the one that I prefer students to use is binom.dist.range because you actually can do this for all of your binomial probabilities. So again, we'll be using binom.dist.range, and I will try to make sure that that's the one I stick with each time, because what happens when we use binom.dist, you have to be careful with if you're using true and false and all that. I feel that students do much better with this binom.dist.range. So let's do some examples. So to use that binom.dist.range, you will enter your n value comma, p-value, so the probability of successes, comma, your min, and then your max. Now, if you do not have a min and a max, and let's say I just want to find exactly a specific value, then you could just put in binom.dist.range. N, P, and then that one value, and that will give you that specific value. You can see here above, I have information on how to use those other formulas. But again, I really feel that students do well with binom.dist.range, and they're not having to remember as much with all the different Excel formulas. So I'm going to try to stick with binom.dist.range. Here we have an example on joint surgery. I'm going to talk through it here, and then I'm also going to have a Excel video for you on how to find this binomial probabilities. So we have a certain type of joint surgery has a 75% chance of success. 3 unrelated patients receive the surgery. Construct a probability distribution for the number of these 3 patients who have a successful surgery, then create a histogram for the distribution. So to do this in Excel, you will type the known information into Excel in an organized way. So what is your N, your P, whatever else you may need. Then make a column of possible X values and label it. Make a column of the probabilities next to your X values and label it. And then for each row, you are going to type binom.dist.range, parentheses, NPA. So I'm going to just mark this out here. So you're actually going to do equals binom.dist.range, parentheses, NP, and then A is that value that you're looking for. So to create the histogram, you're going to select all the probabilities and then click Insert, Column Chart, and then make sure that you just format and label it correctly as we have done histograms in the past. If you would like to look at the video, you can pause here and then go to the joint surgery video for this example. Here you can see the probability distribution table and the histogram. Please, if you have not stopped and watched the example for joint surgery in Excel, please do so, because I'm going to add a little bit more about how to find some probabilities of no more than 2, at least 1, and between 1 and 3, so you guys can see some examples with that binom.dist.range formula. So now that you've watched the joint surgery example in Excel, I would like for you to try this Twitter example on your own. So you can pause the video here so that you can see that problem, and then when you come back, you will see the answers. Here are those answers to the Twitter example, and of course, if you have any questions, please ask in the Teams channel Unit 2 so that I can answer for the class. Let's look at another example. We have the overtime rule in football. So between 1974 and 2011, there were 460 NFL football games decided in overtime, and 252 of them were won by the team that won the overtime coin toss. Is the result of 252 wins in the 460 games equivalent to a random chance, or is 252 wins significantly high? We can answer that question by finding the probability of 252 wins or more in 460 games, assuming that the wins and losses of the games that go into overtime are equally likely. Another way to word this question is, does the coin toss winner end up winning the whole game more often? So in this case, we're going to use that notation for the binomial probabilities. We have our N is 460, our probability of success is 50% or 0.5, and our Q is also 0.5 because of 1 minus P. We want to find the sum of all the probabilities for each value of X from 252 through 460. So that means that we want to find the probability that X is greater than or equal to 252. We can use the binom.dist.range formula to find this answer. So we're going to do equals binom.dist.range dot range. You'll put in your N of 460 and then 0.5. And our min here is going to be the 252 all the way up to a max of the 460 games. And when you put that into Excel, you should get 0.022. This means the probability of 252 or more wins in 460 overtime games is 0.022, which is low because it is less than 0.05. Because it is such a small chance, that shows that it is unlikely that we would get 252 games or more wins by chance. So if we rule out chance, then we're left with the more reasonable explanation that the team winning the coin toss has a better chance of winning the game. To find the mean, standard deviation, and variance for a binomial random variable, it's pretty simple. So our mean is just going to be n times p. Our variance is n times p times q. And of course, the standard deviation is the square root of the variance. So it's the square root of n times p times q. Just remember that significance rule, significantly low values are less than 2 standard deviations away from the mean, and a significantly high value is more than 2 standard deviations above the mean. We're going to look at the football example again and using the parameters to determine significance. So previous example, we had an N of 460 overtime wins in NFL football games. We get that P was 0.5 and Q was 0.5 by assuming that the overtime coin toss does not provide an advantage. So both teams have the same 0.5 chance of winning the game in overtime. Part A, we're going to find the mean and the standard deviation for the number of wins in groups of 460 games. Part B, use the range rule of thumb to find the values separating the numbers of wins that are significantly low or significantly high. And C, is the result of 252 overtime wins in 460 games significantly high? So when we're looking for the mean and the standard deviation, those formulas are pretty simple. So our mean is just n times p. So all you have to do here is 460 times 0.5, and we should get 230.0 games. Our standard deviation is going to be the square root of 460 times 0.5 times 0.5, and that gives you 10.7 games. So for random groups of 460 overtime games, the mean number of wins is 230 games, and the standard deviation is 10.7 games. The values separating the number of wins that are significantly low or significantly high are the values that are 2 standard deviations away from the mean. So we have our mean of 230 games, and we have found our standard deviation of 10.7 games. We're just going to plug this right into our formula. 230 minus 2 times 10.7, and we'll do 230 plus 2 times 10.7. And then you can plug this into Excel, and you're going to get 208.6 games and 251.4 games. So this is looking at that significance, right? So what we're saying is that between 208.6 games and 251.4 games, that's not significant. So significantly low number of wins would be that 208.6 games or less. The significantly high number of wins would be 251.4 games or more. So we got to think back. Our result of 252 wins would be considered significantly high because it's greater than the 251.4 games that we found in Part B. So this is just another way to look at significance by using the parameters instead of the probability. You can now finish your MyStatLab homework, Section 5.2, and your lab manual pages 45 to 47, And of course, if you have any questions, please post in the Microsoft Teams channel and I will answer for the class.